In this portion of chapter 2, we will talk about nomenclature, which is the naming of compounds. This again is a very fundamental part of chemistry, and this is very important. You will need it for throughout chemistry. Okay, so the first thing is what are compounds? You already know about elements, okay? That's all in the periodic table. Compounds are elements combined in different proportions. So in this chapter, we're also going to learn about which proportion things combine in, okay? Not only what is combining. So anyway, there are two types of combinations or bonding as we call it. So the bonding is ionic and covalent, okay? And ionic is a transfer of electrons. It's between metals and non-metals, and there are cations and anions, okay, in ionic bonding. In covalent bonding, it's because of sharing of electrons. It's only between nonmetals and there are no ions present. So think about this. If you have a periodic table in front of you, then bonding is between the left-hand side of the periodic table, which is the metals, and the right-hand side of the periodic table. Whereas covalent bonding is only on the right-hand side of the periodic table, okay? Within ionic compounds, there are two different kinds of nomenclature. One is for what we call the main group elements, and the other one is for the transition metals, okay? So essentially, it becomes three different kinds of bonding, okay? Two for ionic, one for covalent, okay? Some of the rules will be the same for ionic, but there is a different rule for transition metals, okay? All right, so that's what we're going to do. Okay, molecules and formula units. Compounds that are formed because of covalent bonding are known as molecules. Compounds that are formed because of ionic bonding are called formula units. And that is because ions do not exist as just one and one. They form an entire crystal structure, okay? And so the minimum number that you require to form a formula is called a formula unit. Molecules, on the other hand, can exist by themselves in small numbers. So that's why covalent compounds are called molecules, whereas ionic compounds are called formula units. I will be referring to almost everything as a compound. For me, a compound is a combination of elements. But when I say a molecule, that means it's definitely a covalent compound. But I don't call ionic compounds as a formula unit. I just call them ionic compounds. Then there are 7 diatomic gases that you should be aware of. And these have the same names as the elements. So it's a little confusing. And as we go on, we're going to learn about how to differentiate between the element and gas. So for example, H2, which is still hydrogen, this is still oxygen, nitrogen, fluorine, chlorine, bromine, and iodine. So these are still referred to as their element names. However, they are diatomic. Okay, and so in chapter 3, I'm going to tell you how to differentiate between hydrogen as an H and hydrogen as an H2. Okay, but make a note of these, and these are the only 7 diatomic gases that we have. The other gases we have is group number 7, which are the noble gases, which do not form any bonds, okay, for most part. So we will not be using those in nomenclature. Now combinations, okay, how combinations occur. There are 3 different kinds of formulas: empirical formula, molecular formula, and structural formula. Empirical formula is the lowest combination of elements, okay, and so you have H2O, for example, CH2O. Molecular formula is the actual ratio of elements in a compound, which means that I can take an empirical formula, multiply it by an integer, and get the final compound, okay. This one, if you divide by 6, you should come up with the empirical formula. That's kind of the relationship between empirical formula and molecular formula. The final formula is the structural formula, which is a 3D representation. We are going to do this also, but later on in the semester, not right now. In this chapter and the next one, we will be dealing with empirical formulas and molecular formulas. You have to remember that for ionic compounds, almost everything is an empirical formula. For covalent compounds, you can have empirical formula and molecular formula. But for ionic compound, pretty much all the formulas that we have are empirical formulas, which is the formula unit also. Okay, so that's what this is. Here is another example. Let's talk about ionic compounds and let's see what happens. How do you form ionic bond and how do you name ionic compounds? So first of all, if you remember, ionic compounds are formed from metals and from non-metals, which is the left-hand side and the right-hand side of the periodic table. I want to remind you that transition metals are in the middle. Okay, that's the sunken part of the periodic table. The first two groups, which is the alkali metals and the alkaline earth metals, and then starting from boron, group number 3, until you get to neon, those groups are known as the main group element. Okay, and so when I talk about most of the periodic table, we are referring to mostly the main group elements. Transition metals have a different type of reactivity, different nomenclature. Everything is quite different about them. So the main group elements are groups 1, 2 through 8. Okay, not counting the transition metals. Okay, metals lose electrons. Now, whether these are transition metals or main group elements, it doesn't matter. But metals will lose electrons and they form cations. Cations are positively charged. Non-metals will gain electrons to become anions. Okay, and anions are negatively charged. Electrons will transfer from metals to non-metals. If metals are losing electrons, something has to gain electrons. So metals will lose electrons and non-metals will gain the electrons. And then the final unit that is formed should be electrically neutral. If it has a charge, then it will still be an ion. Whether it's a positive ion or a negative ion, that remains to be seen, but it will still be an ion. It will not be a compound. It can still be a compound, but it will still be an ion also. Okay, so group number 1 will always lose 1 electron. So whether you have lithium, sodium, potassium, whatever it is, it will lose only 1 electron. It will form these kind of ions. This is called a lithium ion, sodium ion. Nothing too glamorous here. Group number 2 will lose 2 electrons and form magnesium ion, calcium ion, and so on and so forth. Group number 3 loses 3 electrons and forms aluminum ions and so on. And then starting from group number 5 on the right hand side, which is the non-metals, group number 5 gains 3 electrons, becomes the nitrogen ion, the phosphide ion. Please note the name, phosphide and nitride ion. Group number 6, which is the oxygen group, will gain 2 electrons and become the oxide ion and the sulfide ion. Group number 7, which is the halogens, they gain only 1 electron and they become chloride, bromide, iodide, or fluoride ion. Okay, so these are the anions formed. The cations retain their name, whereas the anions will change their name to IDE, I-D-E. Okay, all right. Now for naming the compounds, all right? We talked about the fact that you add ion, sodium ion, for example, in front of the cation. Regarding the anions, you rename it slightly by ending it with "ide." Okay, so chlorine becomes chloride, oxygen becomes oxide, and so on. When you name the ionic compound, you leave the name of the metal as it is, but you change the non-metal to "ide." So here, sodium chloride, calcium oxide. That's how you would name something. Please note that the name here does not really tell you anything about how many calcium there are and how many oxygens there are in the ratio. That is something we have to work out. Okay, so similarly here, sodium chloride doesn't tell you whether the ratio of sodium to chlorine is 1:1 in this formula. There is a reason for this, and that is that there is only one type of combination possible, okay, for main group elements. That's why we don't really need to tell. When you have calcium and oxygen, calcium gives 2 electrons and oxygen takes 2 electrons. So there is only one combination possible, calcium oxide CaO. In some other cases, there'll be a little bit more ratio, but otherwise there's only one combination possible. There are only 2 exceptions. in the main group elements, and that is for lead, which is in group 4, at the bottom of the group 4, which is lead 2 and lead 4 ion, and then thallium in group number 3, which has 2. You will encounter lead a lot more, okay? So it's much better to remember this one. So how do you form a formula unit? So for example, let's take aluminum and oxygen. If you're asked to form a compound between aluminum and oxygen, you find them in the periodic table. You know that aluminum can be 3 plus and oxygen can be 2 negative. Remember, your final formula must have a charge of 0. There should not be any charges left over. So which means if aluminum gives 3 electrons, oxygen should be able to take 3. If it's not able to take 3, which it's not, you need another oxygen. So working this out, you will see that you will need 2 aluminum, which gives a total of 6 electrons, and 3 oxygens, which takes a total of 6 electrons then. So the ratio is not as simple as 1:1 or 2:2 or 1:2. It can be odd ratios as well, like 2:3. It will never be 2:3.5. Remember that, okay? Because that is against Dalton's atomic theory. Okay, and so you have to make sure you take complete ions and not fractions of them. The easiest way to figure out what the formula would be is what we call the crisscross method. And the crisscross method is that you take whatever ion is on one and change it to the subscript of the other. So for example, you take the cation, aluminum, and you take the charge of that 3 and you put that as a subscript for oxygen. You take the charge on oxygen and put that as a subscript for aluminum. Okay, so you crisscross, and once you crisscross, you will see that you will always come up with the right formula. This one cannot go wrong. This here is a diagram showing you how the electrons are lost and gained in case of forming an ionic bond. And this is what a crystal is called, and that's why ionic compounds actually have formula units, which this is a formula unit right here. Okay, 1 sodium, 1 chlorine, that's a formula unit, but essentially this is the whole compound. Okay, that's how it is called. Okay, so again, remember crisscross method and make sure that the charges come out to be 0. Okay, so now for transition metals. Transition metals are the same as the metals, which means they still give electrons. The only problem is that they give a variety of electrons. So some can give 2, 4, 5, 7, and some of them can give 2 as well as 3. So for example, copper can give 1 electron. It can also give 2. Iron can give 3 electrons, and it can also give 2 electrons. So you have to refer to the ion and indicate how many electrons it has given. So copper 2 plus would be called a copper 2 ion. Iron 3 plus would be called an iron 3 ion. If it was iron 2 plus, which means it has given 2 electrons, then it would be called iron 2 plus or iron 2 ion. Remember, over here you have to put this in brackets and Roman numerals, okay, capitals, not the smaller ones, the bigger ones, and put them in brackets. And this is how you would start for the name. Regarding the ending of the compound, it's still the same way, which means that you still have the non-metal, which is still the ide. The non-metals are still taking the electrons. So that you still end in ide. The only thing is that now, since you're combining iron 3 plus with oxygen over here, the name would be iron 3 oxide. That's what it would be. How do we figure out the charge on this one? We will do that also, okay, later on. Here, if you have manganese 4 plus and sulfide, okay, sulfide is 2 minus. If you were to do a combination of those two, again, do the crisscross method. And so Mn will give its number to sulfur, and sulfur will give its number to Mn, which is manganese. And then you bring it down to the lowest ratio, okay? Remember, empirical formula. And so divide this by 2, and so you get MnS2. But because you started with Mn as in 4 plus, this is manganese 4 sulfide. Okay, that's how you do for transition metals. So any transition metal that you have, will be named according to the Roman numerals. Okay, you still don't change the name of the metal, and you still have to end the non-metal with the "ide." Here is a little bit of a table that you should keep handy in the beginning with you so that you know what kind of ions are forming. Regarding the main group elements, okay, for group 1 is always +1, group 2 is always +2, 3 is always +3, and see, it's only aluminum that you have to worry about. We're not going to worry about bonding for these elements here. Group number 4, carbon is considered to be a non-metal, and carbon can give 4 electrons or take 4 electrons. Okay, for most part, it actually likes covalent bonds more than ionic bonds. But anyhow, so group number 4, carbon has 4 minus, and then as you go to the bottom here, these ones, tin and lead, these are both considered to be metals, and they have both 2 charges, okay, 2 plus and 4 plus. So tin is tin 2 ion, and this is tin 4 ion. Group number 5 is 3 minus, nitride, phosphide. Group number 6, oxide, sulfide, selenide, telluride. And then number 7, which is halogens, fluoride, chloride, bromide, and iodide. And these are the ions. Remember, group 7 takes 1 electron, group 6 takes 2 electrons, group 5 takes 3, group 4 takes 4. Okay, and remember when I was telling you about the main group, all the A's over here, these are the main group elements. These are the transition metals. In case of the transition metals, as you can see, you can have multiple charges or multiple valencies. Okay, so chromium 2 plus, 3 plus, Mn, manganese 2 plus, 3 plus, it can be 4 plus or 5 or 7. You don't have to remember how many charges it can have, but if you're given a compound, you should be able to figure it out. Okay, and we will do that practice in class also. So anyhow, these are all the different charges or valencies that transition metals can have. Now, polyatomic ions. These are ions that are formed from non-metals. So if you look at all of these elements, these are all non-metals, okay? But they combine in such a way that they actually have extra electrons. The extra electrons are coming from metals, which means that these do not really exist by themselves. If you go out and look for a carbonate ion, you're not going to find that, okay, by itself. It is always found in combination with something else. But what a polyatomic ion states is that there is carbon and 3 oxygens which can combine in this kind of a format, okay? And these ions exist, and that's all there is to it. All you have to do is memorize them. This is possibly the only chart and the only slide that you should print out and just memorize, because there is no other way for this one. There is no way out, okay? So all you have to do is memorize this. All the other things that you learn are things that you can understand and you have to work it out. But this one, there is no working it out. Okay, so you have to memorize this. There are a few things that I can give you some clues about, but other than that, memorize, memorize, memorize. So there are 2 positive polyatomic cations. One is hydronium ion. The other one is ammonium ion. The ammonium ion, NH4 plus, is coming from ammonia, which we will learn about it later. NH4 plus really is the more important cation here. The hydronium ion exists only in solution, so we don't really talk about it so much. These 2 ions here, these are very simple polyatomic ions, hydroxide and cyanide, okay? All the other ones are a little bit more complicated, and they have varied numbers of oxygens in them. The OH minus is a negative polyatomic ion, and it's the only one that ends in ide and has an oxygen in it. All these other polyatomic ions, if you look at them, they all have oxygen in them, and they all end in ate, or ite. Okay, it's all ates and ites for almost all the polyatomic ions except for hydroxide. Okay, so this is a little bit exception. That's why I put it separately for you. And these are the 2 only ones that actually end in ides. Okay, the rest of them all end in ates or ites. Okay, so the first two over here are the carbonates, which is the carbonate and then the hydrogen carbonate. If you look at the difference between the carbonate and hydrogen carbonate, it is the difference of a hydrogen. It's actually H plus. So if you add H plus to CO3 2 minus, you add the hydrogen, but you also add the plus sign, and therefore one of the negatives is gone. Okay, same thing happens with sulfate. Sulfate is made up of sulfur. So here we have a sulfate ion, and then there is hydrogen sulfate. Sulfite, hydrogen sulfite. Nitrate, nitrite. Phosphate has three charges, so you have three ions for phosphate. Phosphate, hydrogen phosphate, and then dihydrogen phosphate. This is acetate. And then here are some which are a little bit different: chromates, dichromates, permanganates, and all that. The reason I made two tables over here for you is that this is the one on the left hand side that I need you to memorize, and memorize it absolutely. This table on the right hand side you can use to answer your homework questions and your other assignments, but you don't need to know this for the exam because I will give you these for the exam. But this one you absolutely have to memorize. Okay, one other little point I want to make out over here for you is that there is a difference in the eighths and the ites, and that has to do with the number of oxygen. 8 is always the higher number of oxygen, ite is the lower number of oxygen. So sulfate has 4 oxygen, sulfite has 3. Unfortunately, this doesn't have anything to do with the number of oxygen, only with higher number of oxygen. So for example, nitrate is 3 oxygen, nitrite is 2 oxygen. Okay, so nitrate is not 4 oxygen like sulfate was. It's just a matter of higher number of oxygen and lower number of oxygen. Okay, so these are all the polyatomic ions you need to know. As far as the nomenclature is concerned, their nomenclature is exactly the same as it would be for any kind of cation and anion. These are the anions, and if you have sodium hydroxide, it would be NaOH. If it was sodium sulfate, it would be Na2SO4. That's all. So these names will not change, okay? At least not right now. So you name these ions as they are. So here are some examples, okay, for you. Um, Sodium and hydroxide is sodium hydroxide. Potassium and sulfate is potassium sulfate. Again, do the crisscross. Just do the crisscross. So K goes down there, and the one positive goes down to the sulfate, and the 2 minus of the sulfate goes down to the potassium. So that's K2SO4. Calcium and phosphate. So now this one will be 3 down for calcium and 2 down for phosphate. So it will be Ca3PO4 2, okay, calcium phosphate. If you have a transition metal, then you have to name the transition metals as we did for transition metals, which is that you need the Roman numeral. So this is chromium 2, so you need the chromium 2 over here. The rest is the same, which is hydrogen carbonate and then hydrogen carbonate. And then you can have combinations between polyatomic ions. So for example, the ammonium ion and the nitrate ion, ammonium nitrate. Okay, so that's how you would name for polyatomic ions. So it's very simple, straightforward. We did not change any rules. All you have to do is remember all the polyatomic ions. Let's talk now about naming covalent compounds. Covalent compounds are sharing electrons. So there is no give and take, okay? It's sharing. And we will talk about bonding later on also. But anyhow, the nomenclature standards are pretty much the same, meaning that the first element name is as it is, but the second one will end with an "ide," just like we did for the ionic compounds. But in covalent compounds, what happens is that there are sometimes more than one combination possible. So you have to tell how many number of atoms are involved, whether it's 1:2 or 2:3 or whatever it is. So for that reason, we have to know the prefixes. Okay, and so that's how we tell what the combination it is. So the numbers that we get for prefixes are 1 through 10. And the prefixes are then mono, di, tri, tetra, penta, hexa, hepta, octa, nona, and deca. Okay, and these ones you do have to memorize, which hopefully should not be hard because it is similar to your math. Okay, so anyhow, let's look at some of the examples. for naming covalent compounds. Oxygen difluoride tells you you have one oxygen and two fluorines. Okay, so difluoride, two fluorines. So OF2, tetrasulfur, tetranitride, 4 sulfur, 4 nitrogen. That's the formula. It's as simple as that. And because it is so simple, you want to use it for ionic compounds also, but don't. Okay, keep that name nomenclature separate and keep this one separate. Okay, carbon disulfide, CS2, nitrogen tribromide, NBr3, so on and so forth. Okay, the first element is never ever named as mono. So for example, oxygen difluoride is not mono oxygen difluoride. Okay, the only time you use mono is for the second element. For example, when we have CO, which is carbon monoxide, okay, and then CO2 is carbon dioxide. So for the second element, you can use the mono, but not for the first one. Okay, so that is covalent compounds, fairly easy to do. I will never ask you to form me compounds for covalents because you will not know what combinations to give. So as far as covalent compounds are concerned, you have to give me the name of the compound. So for example, if I give you BCl3, you should be able to tell me it's boron trichloride. Or if I give you the name, you have to give me the formula. You will not have to form the formula for me. For ionic compounds, you can form the formula also, okay, because you do the crisscross method and that's how you do. Now, one of the last portions over here, not the last, penultimate, acids and bases. Okay, first of all, little properties of acids and bases. Acids give protons, which is actually H+. Acids are corrosive. Acids are sour. They are found in mostly fruit juices. And they react with metals to give hydrogen gas. Bases are a little bit opposite of acids, which means that if acids give protons, then bases will accept the protons. Bases are caustic. Caustic and corrosive are just different kinds of burns or reactions that we give, but essentially it is kind of a burn, okay? Bases taste bitter. I would never advise you to taste any of these things, okay? However, for a bitter taste, you might have tasted soap before, and soap is not all that tasty, okay? And that is a bitter taste. And soap is a base, okay? Most of the bases are found in cleaners. So for example, if you look at your homes, you'll find ammonia solution and bleach. Those are all bases, okay? So examples of acids, there are mineral acids, which are sulfuric acid, nitric acid, hydrochloric acids. And these are the strong acids. The weak acids are phosphoric acid, acetic acid, carbonic acid. We'll write the formulas in just a few minutes. And examples for bases, strong base would be sodium hydroxide, potassium hydroxide. Weak bases are ammonium hydroxide. Okay, that's the only one. You should be able to write the formula of all the hydroxides at least. We'll write the formula for the acids. So here we are, okay, with the different kinds of acids. These acids over here, these are also known as binary acids because they're only made of two things, okay, in here. So this, if you look at, these are all halogens. So halogens combined with hydrogen will give you acids, okay. Typically, if I were to give you just HF, you would call it hydrogen fluoride, and that is not wrong. That is absolutely fine. Acids are actually made from dissolving all of these in water. And as soon as you put them in water, they are called acids then. So HF, when dissolved in water, will give you hydrofluoric acid. Hydrogen chloride dissolved in water gives you hydrochloric acid. And then, of course, these two other acids here. So all the acids will be made in water, okay, all the time. These acids over here, these are called oxo acids because they are made or they have oxygen in them. So nitric acid, sulfuric acid, phosphoric acid, carbonic acid. If you look at this right side of these acids, these are all polyatomic ions and these are all hydrogens over here. See, these are also all hydrogens over here. Remember the first definition of an acid. These are proton donors. These are hydrogen donors. So which means that you have to have hydrogen in the acids, okay? All right, naming bases. Again, these are the simple names of the bases like hydroxides. Most of the hydroxides are going to be bases, but then there are some other bases also like carbonates and hydrogen carbonate. They're usually quite weak. They're not very strong. Sodium hydrogen carbonate, for example, that's baking soda, and you can eat that quite easily to relieve yourself of acidity and whatnot. So even amongst acids, there are strong acids and base weak acids, which I gave you in the previous slides. Here is a nice table to have. You can print that out separately if you want to, but this one shows you that here is a polyatomic ion, and if you combine that with the hydrogen, you end up getting the acid. Remember, all the acids are ending in acids, all right? So that's a nice thing, at least, about nomenclature. But the carbonate ion will give you carbonic acid, nitrite ion will give you nitrous acid, nitrate ion will give you nitric acid, so on and so forth. Okay, so keep this table handy also. You can write more on it if you want to have all the acids in one spot. The last kind of nomenclature is naming hydrates. And hydrates are ionic compounds that are associated with water. Remember, this is associated. We're not talking about dissolved. Okay, associated meaning the water molecules are kind of trapped with the ionic compounds. So that's what happens with hydrates. You're going to encounter some of these hydrates in the lab also. All right, so the water actually gets absorbed in the crystals, and those kind of crystals are then known as hygroscopic, which means things that can absorb water. If you've ever bought shoes or purses, you see a little packet in there for a drying agent, and what that drying agent does is it absorbs the water. So that's the hygroscopic substance that you find in some goods. But you can remove this water by just heating the compound. So it's not like it's reacted with anything, there's just associated. So you can remove that, and actually that is our lab, okay, that we'll be doing. In Gen Chem 1 is to remove some of the water from the hydrate, not some, all of the water from the hydrates. So naming is quite easy for hydrates. You still have the name of the compound, and then you add the water, okay, in there with the appropriate prefix. So for example, iron sulfate, which is iron 2 sulfate, but then you have 7 waters associated with it, so you called it heptahydrate. Look at the formula here. This dot over here is kind of in the middle. It's not like a period, which means it's not like this sitting at the bottom of the sentence. It's actually in the middle. So copper sulfate, which is copper 2 ion here, and then the sulfate here, and there are 5 waters, so that is a pentahydrate. Okay, again, remember, these dots are in the middle, not at the bottom, okay, of it. That's how we show that there are 7 molecules of water associated with iron 2 sulfate and 5 with copper 2 sulfate. Here are some names that you will encounter for compounds. These are very commonly occurring compounds, and we don't really have technical names for this, and sometimes you can call them by their common names, it's fine. So in this table, here is the compound like H2O, which is actually water, and if you were to name it, you would call it dihydrogen monoxide. Ammonia, NH3, trihydrogen nitride, but nobody calls it that. Try it with a chemist and you will see they'll go, huh? What the heck? So ammonia, okay, that's what NH3 is called. CO2, dry ice, which is also solid carbon dioxide, but CO2 is still called carbon dioxide. NaCl is called salt, so whenever you say that something is a salt, the first thing you think of is sodium chloride, the edible salt, okay? Anyhow, so just look through these things. I don't need you to know all of these compounds. I need you to know water, ammonia, and one that is not over here is actually CH4, which is methane. Okay, so those ones. But otherwise, systematic names are fine. Okay, for all of this. So here are your keywords and concepts for this chapter. You need to know what these different kinds of formulas are. You need to know what a formula unit is. You need to know the nomenclature of ionic compounds and covalent compounds, transition metals, polyatomic ions. You need to memorize all of those, and then acids and bases. You may have to memorize the acids a little bit. Later on, you will get used to them as you see them more in the lab, but initially you may have to memorize them. Okay, and then finally hydrates.